Still people joining. Just a few seconds and we'll start. Okay, so welcome again. Just a few details before the lecture. The ECCB is a non-profit society dedicated to advancing the science and research of chemical bonding theory in Europe. It serves as a hub for researchers, academics, and professionals in the field. And among its missions, we organize a biannual conference, the European Symposium on Chemical Bonding, that we call C-Bond. The next one will be organized in Brussels next September. And we award prizes and scholarships for research, publishing special issues in scientific journals devoted to contributions in chemical bonding. If you are interested, please visit our website. After the lecture, there will be a 15-minute session dedicated to questions. You are invited to raise your virtual hands, and we will unmute you so you can ask your questions directly. If you intend to do so, please prepare concise wording in advance. Our lecturer today is Renana Gershoni-Poranne, Associate Professor at the Technion in Israel, where she holds a faculty position in the Schulich Faculty of Chemistry. Professor Gershoni-Poranne obtained her academic degrees at the Technion, completing her PhD under the supervision of Professor Amnon Stanger, with a thesis focused on aromatic systems. She subsequently carried out postdoctoral research at ETH Zurich with Professor Peter Chen, where she later became a Branco Vice Fellow and group leader before returning to the Technion as an independent faculty member. And since August 2025, she has been serving as associate professor. Her research lines lie at the interface between physical organic chemistry and computational chemistry, and her group develops and applies advanced computational tools to elucidate electronic structure, magnetic response properties, and structure property relationships in aromatic and anti-aromatic systems. Beyond classical pi aromaticity, her work has addressed non-traditional aromatic frameworks, magnetically induced current analysis, and conceptual foundations that underpin our understanding of electron delocalization and chemical bonding. Her scientific achievements have been recognized with prestigious awards, including the 2024 Creel Prize of the World Foundation, and in 2025, both the Liebig-Lechkerschiff Award of the Organic Division of the German Chemical Society and the Academic Investigator Award of the Division of Organic Chemistry of the ACS. She has been also recipient of Meyer competitive grants from the Israel Science Foundation and the Petroleum Research Fund. In addition to her research, she is deeply engaged in service to the community, serving as associate editor of the Journal of Physical Organic Chemistry, sitting on the editorial advisory boards of the Journal of Computational Chemistry and Chemistry Open. She has co-organized international conferences and plays an active role in the European Symposium on Organic Reactivity. Her invited lectures span leading venues worldwide, including Golden Research Conferences, the WATOC, and other distinguished seminar series. The title of her talk today is Old Ideas, New Tricks, Additivity of Polycyclic Aromatic Systems. And we are especially fortunate to have Renana share her perspective in this ECCB seminar. Please join me in welcoming her. And the floor is yours. You can now share your presentation.
Can you hear me now?
Yes.
Okay, great.
Okay.
So first of all, thank you so much for this very kind introduction. I don't even know where to start. It was very, it was very detailed. So I'm very excited to be here this evening and to share with you some of the work coming from my group. And I really appreciate the opportunity to talk to this community about some stuff that we've been doing. The reason that I call this talk Old Ideas, New Tricks is because, as you will see, some of the concepts that I will talk about have been around for many, many years. And we have recently revisited them using a bit more modern techniques, specifically using deep learning. But they're also, for me personally, it's a bit of an old idea, new trick, because the project that I will tell you about is the very first project that I started working on as an independent scientist. And when I was starting my group at ETH, and then we did some work on it, we left it aside for a few years, and then last year we returned to it again, looking at it once again through the lens of deep learning. And so also for me, it's kind of like a trajectory of a project. So I like to talk about it, and I hope that you will enjoy it as well. So for those of you who are not familiar with my group, I'll just give a kind of a brief overview. We are a computational chemistry group. I would like to say more computational physical organic chemistry group. And so we're very interested in structure, properties, and reactivity of molecules, and in particular molecules that we call PAHs, which stands for Polycyclic Aromatic Systems. And our work spans what I call three different pillars. The first one is more fundamental investigations of aromatic compounds, where we try to put together conceptual frameworks that allow us to understand the structure property relationships of these molecules, and also develop models for example, visualization of the properties of these molecules, such as ring currents, and recently also anti-aromatic molecules as well. Then there's another pillar of my group, which is what we call the data-driven side of the group, where we generate large databases of polycyclic aromatic molecules, and we employ data analysis techniques and machine learning and deep learning models in order to probe the data and understand the underlying structure property relationships, and then not just to get for ourselves a better understanding, but also then to train models that will be able to generate new structures with targeted properties that can be used for different functionalities. And then finally, the third pillar of our group deals with mechanisms and reactivity. This is work that we do in collaboration with experimentalists. Usually what we do here is mechanism elucidation. We look for transition structures. We try to understand the driving forces for reactions in which polycyclic aromatic systems play a key role, whether as a ligand or as the structure itself that is undergoing some kind of interesting transformation. So the story that I'm going to tell you today started in the first pillar, this one here. It was, like I said, the very first project that we did in my group as an independent group. And then recently we transitioned over to this second pillar as we started to apply different types of techniques to see whether we could learn more, get more insight into what we were seeing. So we often say in computational chemistry that I get this a lot from experimentalists, that it's very easy to do computational chemistry because you basically just have to do a calculation and you always get a number, right? You can't fail at doing computational chemistry. And so I oftentimes say that for us, getting the number is not where our job ends, it's where it begins. And so just to kind of give you an idea of how we approach the questions that we look at or that we address in my group, for me, the job that we have is to take the numbers that we get out of a calculation and to actually turn them into insight. And the way that we do that is that we try to put them into explanations using chemical concepts or using frameworks that are intuitive or that speak to mostly to organic chemists in words that they like to use and they understand. So things like atomic charges, chemical bonds, strain, and aromaticity, which a little bit ironically, all of these are not well defined, and yet we use them on a daily basis, and they really make up the language of organic chemistry. And so when we do our computational chemistry work, what we try to do is to build a bridge between the technical aspects and the numbers that come out of the different calculations, try to put them into the kind of framing that uses these kinds of terms so that we can turn our data into something that is intuitive and something that allows us to think about molecules in ways that are easy for us to grasp, in ways that are easy for us to discuss with our friends who are doing experimental work in the labs. So what I'm going to tell you about today is exactly one of these kinds of concepts. It is actually a more well-defined one, but it's one of these concepts that is actually very pervasive in chemistry, even if you don't think about it too much. And it's called additivity. The idea behind additivity is that you can take any structure, and it doesn't matter how big or how complex it is, you can break it up into smaller components. And if you know what each of those components is contributing to the overall property of the entire system, then you can predict the behavior or the property for the entire system simply by knowing the different parts that make it up. And if I want to say that in simple terms, what I would say is that the whole is the sum of its parts. Now, you might not think about it, but you actually use this probably every day in different aspects of chemistry. One of the most common ones is, for example, when you're looking at molecular weight. If I asked you what is the molecular weight of this molecule, which is caffeine, you would just say, well, I have to count 8 carbons, and we have 4 nitrogens and 2 oxygens and 10 hydrogens. And since I know the weight of each of these atoms, then I can predict the weight of this entire molecule. And in fact, it doesn't even matter what the connectivity of the atoms is. As long as you know the molecular formula, you can predict the weight of the molecule. And the reason that that is true is because the weights of the individual atoms do not change depending on how you bind them together. And the weight of each atom is always contributing the exact same amount, regardless of if you have 2 or 3 or 4 different carbons. And that is exactly what additivity does. Another place where you might find additivity is if you want to calculate bond properties. So for example, if you want to calculate the heat of the change in enthalpy of this reaction, then you have to consider that you're breaking a hydrogen bond, a hydrogen-hydrogen bond, you're breaking a chlorine-chlorine bond, you're forming 2 new hydrogen-chlorine bonds. And if you know the bond dissociation energies of each of these bonds, you can predict the change in enthalpy without actually even having to do the reaction yourself. So once again, this is an example of additivity because I knew the contribution of each of these bonds, and I can assume that that this contribution does not change just because of the context in which I'm using it. Some other examples are group properties. So if you've ever encountered Benson's group increment theory, which is very popular in structure activity relationships, you can take a molecule and identify the different components or groups that make it up. You can go to Benson's tables and extract the heat of formation for each of these groups, and then you can predict the heat of formation for the entire molecule without having to necessarily measure it yourself. And then finally, where you might see it even more commonly used is in spectroscopy. So if you've ever tried to predict what the chemical shift will be on a molecule or what the absorption wavelength would be on a molecule, and if you've used ChemDraw to do it, these all use the same kinds of algorithms where you have different tables where different groups have a specific contribution. And if you know where the groups are situated, you can use that specific contribution. You can add them all up and you can get a prediction for a global or molecular property. So that's the idea of additivity. And as you see, it's something that we use every day, probably without even thinking about it, because it's a very powerful tool. If you have a property that is additive, it means you can predict for larger molecules or for molecules that you have not yet managed to make or to measure, you can already predict their properties. And so the next question would be, well, in that case, are all properties additive? And the answer is, of course, no, not all of them are additive. And in fact, we have lots of names for things that are not additive. So all of these different names, allosteric, cooperative, synergistic, emergent, these are fancy ways of saying that the whole is more than the sum of its parts. And I'll just show you one example, although there are more than one, of course, and it's the binding of oxygen to hemoglobin. Hemoglobin is a tetramer that is made up of 4 identical monomers, but as each oxygen binds, it increases the affinity of the binding of the next monomer. So you cannot calculate the affinity of hemoglobin as 4 times the affinity of each of the monomers because the behavior is in what we call in this case allosteric or cooperative. So for me, coming from the field of aromaticity, as you've heard in the introduction, one of the things that I kind of realized when looking at these is that yes, additivity is a very powerful tool, but it is not trivially applied. You can't assume that a property is additive. And so I was very curious, and I was wondering, is aromaticity in polycyclic aromatic systems additive? And since aromaticity is one of those terms that is not well defined and it's very debatable, I'm going to make this a bit more of a targeted question, and I'm going to ask, is the magnetic response of polycyclic aromatic systems additive? And we can argue, probably until the cows come home, whether magnetic response is or is not aromaticity, but that's beside the point because the magnetic response of these molecules is in fact unobservable, and whether or not it translates to aromaticity doesn't change the fact that the response itself does exist. So the question is now, is the magnetic response additive? And just so that we're all on the same page, let me explain a little bit about what I mean when I talk about the magnetic response of these molecules. So this is, of course, benzene. And as we all know, benzene has a pi system. It has these 6 p orbitals that each have an electron in them. And if you place benzene into an external magnetic field that is perpendicular to the plane of the molecule, what happens is that these electrons start moving around in a cycle, which is called precession. And it creates an induced ring current. What we call, in this case, we call it diatropic ring current. And this ring current, as a result of this ring current, what is formed is an induced magnetic field. And the fact that that induced magnetic field exists, we know simply because we know that the chemical shift of the protons on benzene is about 7.27, which is extremely deshielded. And that comes from this magnetic field, that the induced magnetic field that benzene forms because of this circulation of the electrons. This is called the ring current model. It basically says that you can think about a closed cyclic delocalization of electrons as like a wire loop. And if you put a wire loop into an external magnetic field, then you get the electrons to move in a circular fashion, and then you have flux through the ring. So it's the same idea, except now on a molecular scale. So that's what I mean when I talk about magnetic response. Now let's go back to a more fundamental question, which is, how can we even talk about breaking down aromatic molecules into smaller components? Because what we usually do when we think about extended conjugated systems is we think about them as one big system. Because of the delocalization of the electrons, because of the extension of the pi system, we don't really tend to break them down. But what I'll show you is that this is something that has been around for quite a few years. So of course, you're all familiar with the Hickel rule. Which actually was not coined by Hickel, it was coined by Düring, but it was based on Hickel's finding that if you have 4n plus 2 pi electrons sitting in pi orbitals, you will get this behavior that we call aromatic, or these days we would say, in relation to the magnetic response, we would say that they form an induced diatropic current. But if you go, and this is only true for monocycles. Hickel's rule is in principle only applicable to monocycles. But what happens if you want to look at polycycles? Well, it took about 40 years for Clark to come up with his rule that says that the only thing you need to do if you look at a polybenzenoid is to just try to identify the different 4n plus 2 units that are hiding within the system. So for example, here in this resonance structure that I've drawn, you can see here that there are 3 different benzene rings that are hiding within the structure. But of course, if I take these double bonds and I just move them over to the other ring, now I get the 3 different benzenes in the 3 other rings, right? And I can also move the bonds again, and I can get the 4n plus 2 unit to be situated here in the middle ring. So one of the things that we learned from Clark's rule is that the most contributing resonance structure, the one that will dictate the majority of the properties of the molecule, are the resonance structures that maximize the number of disjoint Clark sextets or disjoint pi sextets. And so you might have seen that when people draw coronine, they will draw it with this, what we call a migrating Clark sextet. So it's a sextet that can be in either this ring or this ring, like I showed you before with the 2 separate resonance structures. So this is already a very basic idea of additivity. You're taking a larger molecule, you're breaking it into smaller components, and you're saying that you can kind of predict the behavior of the molecule based on identifying what is within it. So we can identify that there are more Clark sextets, then we can say that the molecule will perhaps be more stable, will have larger homolumo gaps, etc. But it's still not really additive because it's not quantitative. And so one of the other, it was a pretty big step, but it happened quite quickly after this, was made by Randich, who is a very famous chemical graph theory researcher. And what Randich did was he said, well, that's a nice idea, but we can generalize it. Basically what he said is, if we draw resonance structure, what we have to do is we can go around a molecule, and what we're looking for is alternating single and double bonds. And if we can create a complete circuit in which we only go through alternating single and double bonds, then that circuit is one of the conjugated circuits in the structure. And so in this resonance structure, you can see that there is a benzene-like structure here, or a 6-electron circuit here. And then there's another one on this side. So that's another circuit that exists. And you can also go around the entire molecule and create a global circuit. Now, this is just one of the resonance structures of biphenyline. You can also draw this resonance structure, and then you would get this kind of circuit. And basically what Randich said is that you can do this for all of the resonance structures of the molecule. And every time you identify a 4n plus 2 circuit, it will have a diatropic contribution, or what, for in layman's terms, we would say an aromatic one. And a 4n circuit is paratropic. So this is kind of an extension of the Hickel idea, but it's now within a polycyclic system, and also it can have rings that are not necessarily benzenoid. So just to show you an example of how he now made this into more of a quantitative scheme, here's an example from one of his papers, more recent paper. He said if we take this molecule, we have to draw all of its possible resonance structures, and within each resonance structure, we need to identify the different circuits. And if it's, I drew it here in blue if it's a diatropic circuit, and in red if it's a paratropic or 4-end circuit. You do this for all of the resonance structures, and then you count up the arrows. So each arrow along a bond would be a value of 1. And for each of the resonance structures, you sum up all of the arrows. And of course, if they go in opposite directions, they cancel each other out. If they go in the same direction, they sum up. And what you get at the end is all of these different numbers on the bonds. And then you sum that up and you get an overall quantitative evaluation of the molecule. Basically, what would be the strengths of the different bond currents on these molecules. You can even then decompose it back into cyclic contributions. If you identify that this is an 8-membered ring, this is 6, 6, and 4. So this is a really beautiful idea. It's very elegant. And it shows you how you can take a qualitative or conceptual idea and turn it into something quantitative. However, there's several drawbacks in using it if you want to use it in a more robust way, or if you want to use it, for example, like we do for large data sets. And these are some of the issues that come up. First of all, it's just the sheer number of Kekule resonance structures. So of course, as you increase the molecule, you're going to get more and more resonance structures. And within the number of resonance structures, the number of conjugated circuits increases almost to the power of 2. So that's a lot. And you have to consider that values need to be normalized so that we can compare between systems. What does this mean? Think, for example, about benzene and cyclobutadiene. Both benzene and cyclobutadiene have only 2 Kekule resonance structures that are closed shell, which means that they each have 1 on each of the bonds. You add them up together, you would get 2. But we already know from DFT calculations, for example, that paratropic ring currents are much stronger than diatropic ring currents. So how can you compare these two systems if they both have the value of 2? That means that it's not really possible to compare between systems. You need something else in order to normalize it or to correct for that. And then finally, of course, there's the issue that not all resonance structures are equally contributing. If you add them all up in a simple sum, you are inherently assuming that each of them makes a similar contribution. And we know that that's not the case. For example, as I just showed you a few minutes ago, when you have multiple resonance structures, there's usually the Clar structure is the one that is most contributing. So what we wanted to do was to design an additivity scheme that would allow us to understand how these molecules work in a more quantitative way, but also something that would be relatively easy to apply to lots of different systems and in a high throughput way. And so in order to do that, we basically have to ask 2 different questions. The first is, what are the smaller structural components? And the second is, how do they each contribute? So let's focus first on the smaller structural components. Or basically the question here is, how do you break up your molecule? So as I showed you, what Randich did was he broke it up and then looked for different circuits. But I don't want to look for all of the different circuits because there's a lot of them and it just becomes more and more complicated. I would rather look at something that is structural, that is much easier to get out from the structure of the molecule without having to, for example, calculate resonance structures or NRTs or something like that. So what we decided to do is to just break up the molecules into the different cyclic components that they contain. And so, for example, if you take this structure, what it contains are 6 different benzenes, so 6 monocyclic components, 5 different naphthalenes, so 5 bicyclic components, and then it contains 4 different tricyclic components. And as you can see here, the tricyclic components are not all the same. There's this one, which looks like a phenanthrene that we call an angular component, and this one looks like an anthracene, and we call that a linear component. And in principle, you could keep going. You could also identify tetracyclic and pentacyclic components. But the whole idea is to do something where there is a very small library of building blocks that you need in order to predict for larger molecules. And so we stopped here at the tricyclic components, and we wanted to see whether this would be enough to predict for larger systems. So this is how we defined our different smaller subunits. Now we have to go to the second question, which is, what does each of these components contribute to the global property? So just like if you think back to the example that I gave you with molecular weight, in molecular weight, the smaller components are the atoms, and the contribution of each component is the weight of each atom. So now we have different components. We have monocycles, bicycles, tricycles, and I want to know how each of them contributes to the magnetic response of the molecule. And so in order to do that, we went back to thinking about how do we measure this magnetic response, and we use a computational tool that is called NICS. NICS is short for nucleus independent chemical shift. It is a computational method that emulates an NMR experiment. And basically, the idea is that instead of looking at the NMR chemical shift of an atom, like a carbon or a hydrogen, we are looking at what would the chemical shift be if I were measuring it right here at this point. And that's why it's called nucleus independent, because there is no actual nucleus there, and we don't put a nucleus there either in the calculation. We just kind of like take a thermometer that measures chemical shift, and we ask, what is the chemical shift at this point? And the reason that we use this point, as you can see, it is above the center of the ring. And the reason we do that is at the center of the ring is where we expect the strongest magnetic behavior, but we don't want to do it within the ring, because then we also have what we call sigma contaminations. We have effects coming from the sigma orbitals that have a spatial extent within the molecular plane. So we go above the plane of the ring, usually around 1 angstrom, because at that height, we can more safely assume that the sigma contributions are not important, but the pi contributions are still strong. And what we do is we report the negative of the chemical shielding. And if the value is positive, we will say that that's a paratropic ring current. If the values are negative, we'll say that indicates a diatropic ring current. So again, in layman terms, paratropic is anti-aromatic, diatropic is aromatic, and that's what we're looking for. So you can use NICS in different ways. You can, for example, take that one value for each of the rings in the molecule, and then you can have a value per ring. But what we wanted is something that we could actually use to also describe the size of the molecule. And so we used a technique that's called the NICS XY scan, where basically you take a string of these points that follows a line across the backbone of the molecule. And the nice thing about that, or the added value of that, is that now we have a measurement that the size of the measurement is the same as the size of the component. So I'll show you what I mean by that. This is our benzene, for example. In our NICS XY scan, you can see follows this red arrow. And what we get is this series of computed points. And you can see all of the values are negative, because benzene is, of course, diatropic. And you can see that it is most negative right above the center, which is exactly what I told you about where the magnetic response or the induced field is strongest. Now we went and we wanted to look at the next component, which is the bicyclic component. But of course, when we look at the bicyclic component, we have to be aware that it already contains 2 monocyclic components, right? So if we think about naphthalene as if it were 2 benzenes placed together, it would look like this W. But in fact, if you do the NICS XY scan of naphthalene, what you get is this black line. And so if you wanted to describe naphthalene starting from 2 benzenes, what you would have to do is to add this pink line here. This would be what we call the bicyclic correction. And the reason we do this with the correction is because if I took this benzene graph and then I added this black graph, I would do what we call double counting. I would be counting twice the very strong negative NICS values that I get there. But by adding only the bicyclic correction, what I'm doing is I am correcting the term for what happens to benzene when it has another neighboring benzene, but I'm not recounting twice both benzene and naphthalene. We then do the same thing for the tricyclic components. Here, what we do is we start with 3 benzenes because that's what we have. And we also have 2 overlapping naphthalene components. You can see them here. And you can see that for both of these isomers, if we start from just benzenes and naphthalenes, then they look exactly the same. The prediction is this red curve. It's the sum of those contributions. But they're not the same. If you actually do the calculation for the NICS XY scan, you see that in anthracene, the value becomes more negative in the center, which is also what we know about anthracene, that the ring current is stronger in the middle. And in phenanthrene, the ring current is weaker in the middle. And so in order to correct it properly, we have this tricyclic correction for anthracene and this tricyclic correction for phenanthrene. And so overall, what we have is a library of 4 building blocks. And the question is now, is it okay or is it enough to use these 4 building blocks in order to predict larger systems? And so here's a test case. We take a pentacyclic system. And what we do is we just take these 5 benzenes in a row, and then we overlay these 4 naphthalenes in a row. And now we add on these 3 tricyclics, so 2 phenanthrene and 1 anthracene corrections. And then when we just add up the different contributions at each distance point, and what we get is this red line, which is essentially the predicted value. What our model says that this should be the Nix XY scan for this larger molecule if our assumption is correct, and in fact, the behavior is additive. This is the actual scan, the black line. As you can see, it's actually really, really good. Considering the simplicity of the model, it was very gratifying for us to see how closely it matched. And what you see up here in this gray line is the difference between the prediction and the actual calculation. And you can see it's not exactly 0, but that's not an artifact. It's not an error in the calculation. What it's showing us is that everything that is here around 0 are all of the other things in the molecule that we deliberately neglected. So we deliberately neglected these 2 tetracyclic subunits and 1 pentacyclic circuit. Because if you remember from Randich's work, we would have to consider all of those possible circuits. But what we're seeing here is that those circuits really don't make a big difference. And that's why this line is so close to 0. And so basically what this model is telling us is that most of the magnetic response of the molecules is encoded in the first monocyclic, bicyclic, and tricyclic components, the smaller components. And the bigger ones don't really make a big difference, which from a conceptual standpoint is interesting. And it's also very interesting from a practical standpoint, because it means that now with a very small library of building blocks, we can essentially predict the Nix XY scan or the magnetic behavior of much larger systems. So the next thing that we did was to generalize this, to go beyond polybenzenoids into molecules that are more diverse structurally. And so we put in different kinds of heterocycles, and you can see some of them are aromatic, some of them are anti-aromatic. And we can put in more than one, we can put in multiples. And you can see that in all of these cases, the agreement between the prediction and the explicitly calculated Nix XY scan is very good, which shows you that the behavior is quite general. And in all of these cases, the largest component that we actually had to calculate was a tricyclic component, which of course cuts down a lot on computation time. We also did mix and match, so we put in different types of components, and you can see that it works just as well. We also then showed that you can do this for pericondensed molecules, what we call 2D molecules. And in this case, actually what was very interesting is we found that in order to do this properly, we have to consider one more type of building block, and that is the pyrene building block. Because once you start having pericondensed systems, it changes a bit the topology of the molecule. And it was interesting to note that the only thing we needed to add to our library was just this pyrene, and things worked out really nicely. And then finally, what we did is we said, well, if it works so well, why not automate it? And so we made a program where we actually already included the library that we had already calculated of all sorts of different building blocks. And you can download it and use it. You can also extend it with your own calculations if you want, and add in more building blocks, and then automatically apply it to all sorts of different structures and predict their Nix XY scans. One of the things that was very interesting for us is, and this is a lot of time the criticism that Nix gets, is that Nix is an integrative measure, which means that it integrates the entire magnetic field around it, entire current density around the molecule into one scalar, one value at one point, which oftentimes reduces the complexity or hides different features of the magnetic behavior. And so we also managed to show that you could do the same thing with bond currents. So we actually calculated the current density around the molecules. We integrated it around different bonds so we could get a bond current. And you can see here the predicted bond currents that we get for these different molecules. And this is the error. So this is the difference in the bond current that we predict versus the bond current that you actually get. And this is scaled times 5. So that just shows you how small the error is. And so it shows that the behavior that we're seeing is not some artifact that comes from Nix just because Nix is an integrative measure, but it is really describing the magnetic behavior of the molecules. But there's also something else about this that was really cool. Aside from the fact that the magnetic response is additive, which we thought was really interesting and exciting to see, and that we could actually do this in a very kind of streamlined, robust way. But it also says something about the behavior of the molecules. And we're here kind of talking about chemical bonding. So in the context of chemical bonding, what does this tell us about the delocalization of these bonds, which we tend to always think about as being fully delocalized over the entire conjugated framework? What this appears to tell us is that the delocalization is actually quite limited. In fact, the fact that we only need tricycles in order to describe these molecules suggests that beyond the tricyclic framework, the delocalization isn't really very meaningful. And we wanted to see if we could kind of nail that down or understand it better, or even just show it coming from a different direction to make sure that what we're seeing really is true. And so we wanted to be able to show that from a different perspective and also answer the question, how local is local? Because the NIX seems to tell us that it's tricyclic, but maybe, again, maybe this is just because of the way we're measuring it. Maybe it's a different kind of behavior. How can we see this coming from a different angle to make sure that we're not just, maybe incorporating our bias in the way we're doing the NIX XY scans? So in order to do this, we decided to try something out with deep learning, which is a field that we're now doing more and more in my group. And we thought it would be a really nice thing, a nice question in which to apply these kinds of tools. And what we did was we have as I mentioned before, we make databases. So this is our Compass project side of the group. We make large databases. And one of the things we have in our databases, we have all possible isomers of polybenzenoids up to 11 rings. And so out of this database, we took out all of the isomers that have 6 rings or fewer than that, and we took 123 of the 7-ring isomers. And then we took those isomers and we placed them into a grid of NIX points, or basically just, points where we calculate the chemical shift. And we created for each molecule a 3D representation or a 3D data set of the induced magnetic field around the molecule. And then we trained a model. We trained a model on all of these data that included molecules up to 7 rings, and then we asked the model to predict the chemical shielding around molecules that it had not seen before. And so when it had to predict for molecules that have 7 rings, you can see that the error was very small. When it had to predict for molecules that have 8 rings, which is bigger than the model has ever seen, the error was still pretty small. But as we went to larger and larger systems, the error really exploded. And if you look at that, the first thing you think of is, well, that means that your underlying assumption is wrong. Because if the behavior is additive, then it should not grow as the molecule grows, right? That appears to indicate that the size of the molecule is important, meaning maybe because the delocalization gets bigger and bigger, and therefore you're missing out more and more information as you get to larger molecules. But these 2 smart guys, undergraduate students, Yair and Aviad, who were doing this project with us, said, we actually think this is not necessarily a chemical issue, this is a technical issue. And the technical issue is that the graph neural net does not know how to generalize from smaller graphs to bigger graphs. And so how can we solve that problem? And this is what we did. We took a molecule, and each molecule, like I said, is surrounded by these NIX points. And for each NIX point, we found which ring is it closest to. And then what we did is we defined an area around the ring that it is closest to. And we call this a hop. So a 1 hop means I go out by 1 ring, like a radius of 1. A 2 hop means I go out by 2 rings. And you can see that for the same molecule, if I have a NIX point that is associated with this system, with this ring, or a NIX point that is associated with this ring, their 2 hop radius actually gives a different fragment of the molecule. But then what we did is, what we give the model as input is we give that NIX point that we want to predict, and we only give this 2 hop fragment. So the model thinks that it's trying to predict for the NIX point in the vicinity of this kind of molecule. And when you do that, this is what happens to the errors. And that already tells you something. If the model did not need to know the entire structure of the molecule in order to predict what is happening in the system, that already tells you that it doesn't really matter. Whatever is happening far away doesn't really impact what the NIX is reporting, or what the chemical shielding is at that point. So that was already a good indication. Now, of course, the fact that now the error is also very small tells us that indeed, even though we only trained on molecules up to 7 rings, now we can actually predict up to 15 rings, which is again an indication that the size of the molecule is not important. All of the physics or all of the chemistry, all of the information that we need is already within the smaller components. So just to show you what that looks like, this is a molecule that we tested out. This is the contour plot of the ground truth, or the actual predicted chemical shielding. And these red lines are the predicted chemical shieldings. And this is just when we add in the colors, you can see that there are areas that are, of course, have stronger values and those that have weaker values. And this is the error. So of course, the error is always strongest or largest in the plane, because that's where the values are also the largest. But as you move away, you can see that the errors are extremely small, and they're always a fraction of the strength of the field. So I told you we usually measure at around 1. You can see that the errors at around 1 are really meaningless. So it means that the model is predicting well. But remember that one of our questions was, how local is local? And up until now, we were using a model that was trained on up to 7 ring systems and predicting for larger systems. But we said, let's keep cutting it down. Let's train a model that has only seen molecules up to 6 rings, and then ask it to predict for larger systems. And then a model that has only seen up to 5 rings, and then a model that has only seen up to 4 rings. And as you can see, that we keep decreasing the size of the molecules that the model has trained on. The error does go up a bit, although I would say that this is not very meaningful. This is within 2 angstrom of the molecule, about 1 ppm, 1.5 ppm is within the margin of error of the DFT calculation anyway. But the way that it goes up suggests that this is not a difference in what the model is seeing from a chemical standpoint. It's just because now the model has less data to train on. So this is the result of having fewer data in the training set. And then we went, and just so you understand that when we did this model, the model 4, the orange one, this is the entire data set that it was trained on. It has five tetracyclic molecules, and it has these the basic building blocks that I showed you before. And with this information, it is predicting for molecules that are 15 rings. And that tells you that it really doesn't matter that the molecule is that large. It doesn't matter. It doesn't change the underlying behavior of the local behavior of the rings. And then we went to the final step, which was the tricyclic components. And then we saw this. And of course, that doesn't look very good, because you think, oh, that probably indicates that we went a step too far, that the model cannot predict if you only give it tricyclic components. But I have very strong confirmation bias, and I believed the previous results that we had. And so we went digging into this, and we thought about what are we actually doing when we go down to the model 3? We are removing all of these molecules. Now the model is only trained on these systems. What is the most important thing that is missing? It's missing this branching point. Because everything else, all of these other structures, you can make by adding together these smaller components, but we cannot model a branching point if the model has not seen it. And so we took a closer look at this model 3. And now we asked it to predict for the molecules that do not have branching points, and then to predict for the molecules that do have branching points. And you can see exactly where the error is coming from. It's coming from the branching points that the model 3 does not know how to deal with, because it wasn't trained using this kind of component. And then if you put all of this back into the same context, you see that the model 3, when it is asked to predict only for molecules that are similar to what it has seen before, meaning unbranched, it does just as well as the other ones. And again, the loss in accuracy, which is quite consistent, comes from loss of data in training. And so overall, I believe that this shows that the idea of locality in these molecules is indeed supported. What we saw before using our NixXY scans and additivity now has been kind of reinforced in a completely different way. And again, it shows that the tricycles appear to be the minimal unit that you need. Of course, if you want to do branching, you need tetracycles, just like if you want to do pericondensed, you need pyrene. It's because these different components encode for a different topology that you just need to show the model. You have to have it somewhere in there, otherwise the information is missing. So with that, I'm going to wrap up. And what I've shown you today is that the delocalization in polycyclic aromatic systems appears to be meaningful only up to tricyclic subunits. And we've shown that in different ways coming from these molecules. And of course, we've shown it coming from the magnetic criterion. You could also try to look at it through different electron delocalization indices, but I believe that the magnetic criterion at least does support this behavior. And I think that it's quite obvious that additivity is a very powerful tool, and that when you can show that it works, it not only teaches you new things about the molecules or the systems that you're interested in, but it has a lot of practical importance, because we can then automate predictions. We can look at molecules that we do not have access to either computationally or experimentally. And finally, this is something that we've learned a lot in my group, is that if you want to do anything with machine learning or deep learning, it is extremely important to have domain knowledge. Because if we had done this project coming in without any expectation or any knowledge of these molecules, then from the very first result, we would have assumed that our hypothesis is wrong and therefore there's nothing left to do. And so I think that that's an important take-home message for all students who are maybe interested in going more into this direction. So I'm going to just wrap up by thanking my amazing group for all of the great work that they do. These are the current group, and these are former students and postdocs. And of course, I also want to thank these students who worked with us on the project that I talked about in collaboration with Professor Alex Bronstein from the Computer Science Department, who is also a great collaborator and a great friend. And I'm very grateful to the funding agencies which have made this work possible. And if I managed to get you at all excited about polycyclic aromatic systems, please feel free to reach out to me to ask more questions, to discuss. And we also have open positions in my group. So if you're interested in that, you're also welcome to reach out. And thank you very much for your attention.
Thank you so much, Renana, for this wonderful lecture. I'm sure that there will be several questions in the audience. Please raise your hand if you are interested in asking something to Renana. Maybe while the audience decides. Okay, so Ralph, I think you can now unmute yourself. Can you do it? I cannot hear you. Ralph, are you there? I think that you can turn your mic on. No. Well, Edu, while maybe you can try to talk to Ralph on the chat. In the meantime, I have a couple of questions, so maybe you can answer
Yeah, of
some of them.
course.
Yeah, I'm interested in checking how dependent your results in the first part of your lecture are on the path that you follow. So you have been showing straight paths, and
Yes.
maybe in heteronuclear or heteroatomic systems, the straight path is not necessarily the only one that you can imagine. I guess that the results are not very dependent on that, but a few words on it.
So, so here's what I'll say. So in these kinds of molecules, which we kind of call 1D molecules, there's only one way to go. You can start from the left or start from the right, but it's the same thing. The interesting things come out when you look at these molecules, where you can take, for example, here we did a circular path and here we did a zigzag path, just to show that it does not matter. The only thing that you then have to consider is when you build up the prediction, you have to put the components in the same order. And that's really the only thing. But and sometimes it's just a little bit easier, a little bit harder technically, but there's no difference, because the behavior, if like in this case, we basically are taking a path through a three-dimensional field. So it should not matter. It's a smooth magnetic field. It should not matter which path you take. The discontinuities simply come because the field actually extends beyond the ring, but we're truncating it at the ring borders in order to make the additivity a bit easier to do. But it does not matter. I would also say that in principle, NICS is not very sensitive to the method that you use, the level of theory. It is very sensitive to geometry. So if you get an incorrect geometry, the values can be different. But you can, if you take the same geometry and you do the calculation with different DFTs, the results are extremely robust. Also basis sets, by the way. It's also not very sensitive to basis set.
Okay, and then have you imagined another measure, not the NICS, but any other of the many measures that have been proposed for measuring, let's say, aromaticity to check whether this additivity also holds with some of
It's
these?
it's a great question. So I will say you have to use a measure that you can actually add in a spatial way, right? Because every other measure that you have, for example, if you look at HOMA, which is geometric, you have one value for per each ring. And
Yep.
so how would you add it for different rings? You don't have a value, you don't have a way to measure for multiple systems, multi-ring systems. You could try it, but then like in a like instead of having a smooth line, you would have maybe pointwise for each ring, and then you would have to do calculations for that. We've never tried it personally, also because in our experience, HOMA doesn't do a very good job. We did try to do this also with orbital coefficients to show the additivity coming from orbital coefficients, and we had a decent match, but not very great when we were using Hickel theory or extended Hickel. But no, we haven't tried other ones other than that. Mostly for the reason that the ones you have are either global, like energy, or they're per ring.
Okay. Any other question from anyone in the audience?
Angel, Ralph cannot unmute himself. His mic does not work, but he wrote down the question, so
Okay,
I can
so
ask.
you can read it. Yeah.
Yeah. So he asked whether in the additivity scheme you can incorporate 5 or 7 member rings or more complex arrangements of the ring. Which is
Yeah.
the limit?
Okay, so first of all, you can see there are 5 ring systems here. You could also do 7. We just didn't because we didn't think about it. But what I would say what's important to know that if you start adding complicated anti-aromatic structures like pentylene or something like that, it probably won't work as well because this works on you need the individual rings. And for example, in pentylene, the monocycle is not aromatic or anti-aromatic on its own. It's only in the double ring system. So I will say I don't think that this is necessarily applicable to everything, but it is applicable in a broad sense to these kinds of components. And so we do have 5-membered rings and both aromatic and anti-aromatic ones as well. And then in terms of a more interesting arrangement, I assume you might be thinking about pericondensed molecules because catacondensed, they're not, I mean, there's only one way to connect them. There's not, or branching, there's not that interesting. The pericondensed, which is what I showed here, you can also start to have more interesting structures. And yeah, as I've shown here, we've done it, but we didn't do it in as much of an extended way because it was more of a proof of concept than trying to make it into like a very usable tool.
Okay. More questions? No?
I have a question actually myself, Angel, if you would allow me.
Yeah, of course.
And Roberto is also asking some
Yeah.
questions. So, well, mine is relatively short. So, well, very nice talk, Renana,
Thanks.
as always. I mean, you've come a long way since the first calculations of NICS scan, and really everything looks like in a great shape.
Thank
So,
you.
out of curiosity, you mentioned just recently that you use extended Hickel. So, did you use extended Hickel under, let's say, with an external magnetic field as well to do these calculations?
No, this was a while back. This was back when I was
Okay.
at ETH, so you'll have to excuse me that I'm also a bit rusty on it. What we were trying to show was whether we could see additivity also in the coefficients of the molecular orbitals. So in
Okay.
that case, we did
Yeah.
not do any magnetic perturbations or any kind of field addition. We were just looking at the ground state orbital coefficients and trying to see if you take the coefficients of benzene and benzene, for example, will you create naphthalene? And I think the truth is it would not work because of symmetry. The symmetry changes. And so we saw that there were some patterns, but it was not, you couldn't do it in a quantitative way. And maybe if we had done more work on it, we would have figured it out. But at some point we gave up on it and we moved to other things. So like I said, this is a project that I kind of, we kept aside for several years and now we revisited it in under a new direction. But I think it would be very interesting to see that.
Yeah, no, I really like, let's say, doing things at the Hika level because then you have, let's say, the simplicity of the method will not allow you to do very realistic calculations, but you can actually gain lots of insights. And
I completely agree. I think
yeah,
that's the beauty of the Hickel method, and it kind of cleans out a lot of things that we don't really care about too much anyway.
agree. Thank you very much, Rana.
Okay, Roberto, can you unmute yourself
Yes.
or not?
Do you hear me?
Yes, we are listening. Yeah.
Thank you for the talk. I love it.
Thank
I
you.
have a, I have a question about the locality. You comment on the 3 ring units is what you define by locality, but I don't understand. Can you comment on why 3 and not 4 or 5? What makes 3 ring units special in comparison with 4 rings, for instance?
Well, I don't know. I can tell you my hand wavy approximation. I don't, because I did not actually go into depth of why 3 and not 4. But since we've come up with this, I've seen more older literature, but I've also seen other people doing newer work on other things. And what has been shown, for example, in annulenes, is that as you go beyond 14 electrons, the aromatic stabilization energy drops precipitously, which means that there isn't really much aromatic stabilization benefit in delocalizing beyond 14 electron circuits. And so this was shown in annulenes, and I think that it's kind of similar here, even though the molecules are not annulenes. If you have to ask me, I think that would be my guess, but I did not do any explicit research into trying to identify why 3 and not 4.
Okay.
I can just say that phenomenologically from the data, it seems very consistent that the 4, you just don't need it.
Okay, I see. And also have a second question. That applies for linear molecules, linear chains, but what about 2D materials?
Yeah, that's what I have right now on the screen. So
Okay.
you can see some examples that we did here where the molecules are pericondensed or 2D, and it works.
Okay.
It does work. Again, here we only have a few examples because it was more of a proof of concept. But so I don't have the same number of examples, and we didn't automate it like we did for the catacondensed, the 1Ds, which are easier. But I think that in principle it should work. It's just more technically difficult to add these together. You have to create more, but like the library that you need to make is a bit bigger because you also need tetracycles, the pyrene type of tetracycles. And so it makes it a little bit more labor intensive.
I see. Okay. Thank you.
You're welcome.
Okay, I think that Pedro has another question, so maybe you can unmute yourself also. We cannot hear you. Do you have any problem? If so, write your question in the chat.
Okay, Pedro said sorry. I don't know if
Sorry,
that
so
means that
maybe he has not any question. Okay.
Yeah.
Is okay. So any other question from the audience?
Oh, wait. No, he actually have a question.
Okay.
He just wrote it.
Okay.
I wonder what is the effect of planarity, Pedro
yeah.
asked.
Oh, that's a wonderful question. Okay, so I'll put it this way. The effect of planarity, I'm assuming that maybe you mean in the case where the molecule goes from being very planar to maybe being helical, or maybe being somewhat distorted, if I understand correctly. So we actually did this. I didn't show it here, but we also did this in what I call 3D. We showed that it works also for helicenes. So the only thing is that then your building block should also have the slight curvature of the helicene component, the helicene molecule. So in the helicene molecule, for example, if you have something like this, you need to make your library of phenanthrines also have slight curvature if you want to get it quantitatively correct. The truth is, however, that helicene is very similar. I mean, even if you used the planar building blocks, you would get a pretty good matching. It won't be perfect because the curvature does slightly reduce the overlap of the orbitals, and so you have a slight impact on the magnetic response, but it's very small. And so you could get a really good estimate with the planar building blocks, and if you used curved building blocks, it would be perfect. And I don't have it on the slides, but we did it. I hope that answers the question.
Okay. So I guess there are no further questions. If this is the case, maybe we can just stop here and thank Renana again for her beautiful lecture.
Thanks
And
for the invitation.
okay, no, not at all. This is it. We will soon announce the third lecture as soon as we have all the information. Please take a look to the webpage of the European Committee. And don't forget that the Seaborn conference will be held in Brussels in a few months. So we can meet there, all of us together, and share all this interesting stuff. Okay, so it's been a pleasure. Thank you very much. And this is it. Bye-bye.